our first speaker today. We have Todd Amundsen. Todd has been at Bonneville Power Administration in energy efficiency for over 21 years. And for much of that time as a customer service engineer to the Westside utility customers. He has been managing the BPA measurement and verification protocols and guidelines and is part of the team in the design and administration of the Energy Smart Industrial Program. Todd's current title is Industrial Engineer Technical Lead. And Todd, I'm going to go ahead and turn this over to you.
Thank you, Maggie. Good morning, everyone. Welcome. Yes, today, Bonneville Power Administration and ACEEE presenting an industrial heat pump overview. And accompanying me today is Ed Ryder, the American Council for an Energy Efficiency Economy. Ed is the director of the industrial program at ACEEE, and in this role, Ed develops and leads strategic vision for the industrial sector, shapes the research and policy agenda, and convenes stakeholders to accelerate energy efficiency and carbon emission reductions. Prior to ACEEE, Ed worked at Dow Chemical for 31 years in R&D, business, environmental, and sustainability roles. Ed earned a doctorate in chemistry from Michigan State University and a Bachelor of Science in Chemistry from Marietta College. So yes, again, for those of you just arriving, we will be recording this webinar. All are muted here, so please keep your questions into the chat function. Be monitoring the chat function in the chat box. Thank you, Steve Martin, and addressing those as time allows, but mainly aiming to answer those at the end of the webinar. And any questions that we don't address, we'll follow up and get an answer to you directly. BPA's Energy Efficiency Engineering and Industrial team has supported ACEEE's recent industrial heat pump research. And today's webinar is intended to build awareness of industrial heat pumps, or IHPs, and provide high-level technical training to our utility customers. Here's a look at the agenda, and I'll note that, we'll have ESIP manager Tony Simon present a little bit there between transitioning from me to Ed. And for a short warm-up icebreaker to test your chat box skills, can you please respond yes or no to the question? Do you have a heat pump water heater at your home or place of residence? I'll verbally answer no from my near 20-year-old home. I say that because I can't walk and chew gum at the same time. We will tally those responses and try to share responses at the end. I do see a not yet. That's a great answer. Okay. Industrial heat pumps may be familiar technology to many of you that go back decades. I can recall growing interest in them during my college years and early in my professional engineering career in pulp and paper. There were EPRI-led pinch studies at industrial plants that identified industrial heat pump opportunities, and many of those are still on bookshelves or filed away in cabinets. We know the market for industrial heat pumps has evolved more rapidly in Europe and Asia. Several of the key drivers are becoming more front and center domestically and in the Pacific Northwest industrial sites that are likely early adopters are motivated by these four factors shown here. The opportunity to utilize waste process heat, minimize losses, and applying the basic premises of replacing fossil fuel primary energy source with a clean electrical energy source. Focusing on the fact that we're moving heat around, this simplified process shown here is a classic vapor compression cycle represents recycling heat, absorbing heat from one low temperature reservoir, which we're calling waste heat. Typically, they go into the atmosphere or down into the sewer, while heat is rejected to a high temperature reservoir as process heat, where it's effectively supplying heat to a process. The work input, represented as a green lightning bolt, is from electrical energy driving a compressor with a working fluid, which includes many options, including CO2. Plus, we can't forget the auxiliary fan and or pump equipment on coils or heat exchangers that are represented by the blue and red curly cues with arrows at one end. Return on investments on these emerging technologies are looking more attractive, and we're exploring opportunities to increase electrical energy efficiencies of these to lower facilities' operating cost. So through BPA, BPA has a core mandate to acquire cost-effective energy efficiency through measures that are identified by the Council. The agency also has supported emerging tech. BPA's EE Emerging Tech, or E3T, has been in existence for decades. My colleagues that work in this area have done outstanding work during that time. In the past decade, there's been a focus on commercial heat pump water heating systems. Effectively pooling resources with other parties, which includes our utility customers, California IOUs, NEA, EPRI, etc., create a knowledge-based research to a product development process where the knowledge is transformed into products, to product adoption into the market. Success, but it doesn't happen overnight. There are strategies for developing resources to benefit our utility customers, such as tools, specs, qualified programs list, and eventually energy efficiency measures for region-wide deployments, such as the multifamily measure that's planned for 2023, there at the bottom. We want to represent a system focus here. That's why there's a big red X on the equipment COP listed for the heat pump water heating compressor component. Package system can be scaled rapidly across multiple markets, multifamily, agricultural, commercial facilities. 3 commercial heat pump water heating system configurations are represented here. 1, mounted on a large rooftop skid. 2, snug in a small closet. And 3, one located on a skid in a large garage. We expect that industrial heat pump system configurations will vary as well. The map shown here reflects recent data compiled by ACEEE at the state level for electricity to natural gas price ratios. The example calculation shown here uses a 5-cent electrical energy rate to a 50-cent per therm natural gas rate with that standard 29.3 kilowatt hour per therm conversion factor. And it results in an attractive dark blue state, no politics here, scenario. Washington State, for example, overall fits this scenario. Of course, if we zoomed in to a public power level across the entire Northwest, we could see even more favorable economics due to the very competitive electricity pricing. A ratio of less than 3 provides a more traditional 2 to 3 year payback. But we'll note, there are industries out there that are accepting higher paybacks for a decarbonization project. This graph represents the electricity to natural gas ratio trend, which is based on EIA data source for the state of Washington. Over the past year, that ratio has been less than 3 for all 12 months. And it's likely that industries are beginning to plan for the higher natural gas prices and making capital decisions on that basis. We believe industrial heat pumps will have attractive economics for certain applications. There are really 3 common applications for industries that we'll term as heat sinks, though some niche applications likely exist. There's hot water, there's hot air, and there's low pressure steam. Hot air could also include space heating too, and low pressure steam could include humidification and clean in place process systems too. A good candidate is going to have a heating need in one of these 3 categories, which is called a heat sink. We need a heat source to provide that heat. Recently, Energy Smart Industrial has investigated 2 separate facilities expressing interest in industrial heat pump technology. I'll now turn it over to ESIP Manager Tony Simon.
Hey, good morning, everyone. Thank you, Todd. We are really excited about this technology and looking forward to our first application of capturing and utilizing waste heat using industrial heat pumps. While the program has yet to support the installation of an industrial heat pump as an energy efficiency project, we've identified 2 sites who had some interest this year. One is a food processor whose heat source is a condenser in an ammonia refrigeration system, and where the heat sink is dry air for their powdered milk drying process. And 2, a lumber producer, where their heat source is warm, moist air at the outlet of the kiln, which is typically exhausted as waste heat coming off the kiln, and where their heat sink is preheating the incoming air for the kiln drying process. While heat pump technology in industrial applications is emerging, it's promising to report that there are currently some vendors in the market who are currently selling industrial heat pumps for lumber drying applications. This would be a replacement of a conventional biomass or fuel-fired steam system which exhausts waste heat to the surrounding area. Heat pumps in this application can reach the process temperatures needed to dry the lumber with a higher efficiency as well as being scalable technology. So we'd like to help you visualize one of the examples we provided. So in this practical application, we're showing this example of a closed cycle heat pump used for lumber drying kiln. In this process, a conventional drying would be performed using processed live steam from a fuel or biomass-fired boiler. As heat drives off moisture from the lumber, it cools slightly, but then would normally be exhausted from the kiln stack. For a heat pump installation like this, the heat pump provides hot, dry air as it comes in contact with the lumber product, drying it, and instead of exhausting the moist air, it is returned to the heat pump where the remaining process heat is recovered, recycled, dehumidified, and then reheated and re-entering the process as hot, dry air again. You'll also notice the arrow of water removal, which is needed because the dehumidification results in condensate, which needs to be removed, which is very similar to what you might see with the heat pump water heater application. Thank you, and now I'd like to hand it off to Ed Ryder from ACEEE.
Yeah, just following up on the applications that Tony mentioned in the lumber area as well as in the food. I'll return to that in a minute with some case studies, but first wanted to give some sense as to where the energy load is in BPA's service area, which you can see is largely associated with pulp and paper, wood, and you can see food applications come in there as well. And in addition, there are some heavy industrials such as cement, primary metals, and chemicals also major energy users in BPA's service area. Next slide, please. So process heat is a large cross-cutting opportunity in the industrial space for reducing greenhouse. And in fact, in this, you can see that in BPA's service area, again, it's lumber, paper, food that account for a large portion of the process heat. Hence, this is an opportunity space for industrial heat pumps. Next slide. So reasons why industrial heat pumps now, as I mentioned, electrification, efficiency, science-based targets, and I'll also note that there have been a number of technology advances in industrial heat pumps in the last few years. In particular, it's got new working fluids, lower greenhouse gas potential working fluids that are more effective and more efficient as well. And they also have the opportunity now to have activated heat pumps, which can recycle some of the waste heat. Additionally, I'll point out that there's multiple benefits that heat pumps can provide outside of energy or greenhouse gas reduction. And those are speed of response, improved control, for example, and others. Those type of non-energy benefits are oftentimes very important for the justification case for the industrial heat pumps in multiple applications. Next slide, if you would, please, Steve.
Yes.
So it's important to also consider the range of process heat that we're talking about relative to temperature. And this suggests the candidate field for industrial heat pumps. And you can see on this slide that for food, pulp and paper, and chemicals, there's a fair amount of process heat that's under 200 degrees centigrade. That is the attractive range for current advanced industrial heat pumps. And that range continues to go up as more developments occur as well. And you can see that there's also applications in other industrial sectors, but today we'll talk principally about the food as well as the pulp and paper applications. So next slide, if you would. This slide shows the range of industrial heat pumps again, where you can see that there's different ranges for those industrial heat pumps. And you can also see that there's multiple different types of industrial heat pumps. Those types, we won't get into the specifics today, but just bear in mind that there's multiple different types, multiple different applications that we could discuss. Next slide. So on the next slide, this is a little bit of a build. We just wanted to point out here that in your typical application, you would be supplying a boiler with a fossil fuel. That fossil fuel provides that heat to some type of process, and then the waste heat goes to the atmosphere. In the industrial heat pump application, conversely, what we're looking at is the industrial heat pump is supplied by electricity, but instead of all of the waste heat that might be generated going to the atmosphere, a portion of that is recycled back into the system through the industrial heat pump being able to use that energy that would have been normally exhausted. That allows a coefficient of performance that's much higher in the industrial heat pump case than it was in the boiler case. You can see on this slide, the COP for the industrial heat pump case is around 4, and that for the boiler would have been around 0.83. Next slide. So Todd had mentioned that thanks to BPA and a few others, we had done some early research on the applicability of industrial heat pumps in the U.S. And we had studied 3 different industry groups, paper, food, as well as chemicals. And we had studied several different unit operations. And the study of the unit operations was key because we were looking to provide information that engineers would use to help justify the industrial heat pumps and to help set the stage for pilots, which we'll talk about later. So again, those unit operations, there's several. I'll show the roll-up of the results from that study in just a minute. So next slide. This shows the high-level picture from that study showing that overall, we found that the industrial heat pumps could provide a source energy savings of 26 to 32%. So that's the net savings. That is that there's going to be natural gas savings and some use of electricity, but net, you're saving considerable amount of energy. And we also found that the payback for compression-related heat pumps could be under 3 years, depending on the price of natural gas. In this case, we had used $4.50 per million BTU. Across the 9 unit operations studied, we found that we could save overall some 400 trillion BTUs per year, and the process heat in general that could be saved was in the range of 40 to 57%. I'll note also that there's substantial CO2 savings that we showed in our study, somewhere on the order of at 9 to almost 13 million tons of CO2 per year. Given the current carbon intensity of the grid nationally, and of course in the Pacific Northwest, this could be even better. Next slide. So this next slide shows tornado plots of the potential energy savings as well as the CO2 savings. Energy is on the left, CO2 is on the right. And in this case, the natural gas savings are in red, and the electricity usage is in green. The point of showing this slide is twofold. One, showing that there's substantial natural gas savings depending on the type of industrial heat pump that you use, but overall there's substantial savings. And then again, depending on the type of industrial heat pump, some electricity is used. On the right-hand side, pointing out here that there's substantial savings in CO2, and that the green bars, which is the electricity used, will become smaller the more the electricity grid becomes greener. And so those bars in the Pacific Northwest would be pretty small to begin with. Next slide. So following up on Tony's introduction of a couple of applications in food as well as in lumber, we wanted to point out a couple of case studies that we had found globally for use of industrial heat pumps in these applications. The first one shows powder milk drying by a spray drying, and this was from a plant in Denmark. But what you can see here is that the process is preheating of the milk powder, and it shows that the payback is under 3 years again. The size of this unit is about 1.25 megawatts, and this was compression style heat pump. Looking back at the previous slide, this would be an MVC, mechanical vapor compression type of heat pump. In this case, I'll also point out the energy savings were significant, and the coefficient of performance at 4 was also very attractive to the end user. Next slide here, you'll see just a schematic, and we wanted to point out that this case, this is a hybrid heat pump, in that the heat pump is being used to take the temperature from 40 to 80 degrees C, and then additional boiler comes in to take it up to 150 degrees C. A point of showing this is that hybrid applications are certainly also something to have on the radar. The next slide, you'll see for the timber drying application. This is one from Canada that, again, high temperature being used here. This is upwards of 115 degrees C. Again, a compression style heat pump. And it shows that since about 2011, it's operated around 2,000 hours per year. Again, the coefficient of performance here is also fairly high, showing very good efficiency. On the next slide, wanted to point out that there are a number of vendors globally that are providing these industrial heat pumps, especially the advanced industrial heat pumps. And on the right-hand side, Trane Johnson Controls, of course, I'll point out, are domestic suppliers that have collaborations with some of the international suppliers to bring some of these industrial heat pumps to the U.S. And in some cases, they've said that they have a route to supply them domestically and to make them domestically as well. We also wanted to point out the range of thermal capacity of these heat pumps, as you'll see in the next slide. And you can see that they range considerably towards the upper end, looking at multi-megawatt systems. And you can see the temperature ranges for these systems are also across a wide range, but certainly higher than what would have been industrial heat pumps from several years ago. We also wanted to point out, sorry, there's a plane going overhead. We wanted to point out that what we're looking for in this work is setting the foundation for pilots. And the foundation for pilots allows us to accelerate the learning that we have for the industrial heat pumps, allows users to get their eyes in on the industrial heat pumps and to think about applications as well. And we're in phase 2 of this work, which is setting the foundation. Phase 3 will actually be the installation and evaluation of the industrial heat pumps. So with that, let me pass it back to Todd, and I'll apologize for the communications challenges here.
Well, thank you, Ed. Appreciate you hanging in there and having a backup plan. Sum it up, we've identified success factors. These are characteristics you can look for in identifying industries that may be good candidates for an industrial heat pump. The first three factors are site-specific physical attributes: process heating load, available waste heat, potentially even a neighboring site, and simple design integration, which for new construction there are major retrofit opportunities. The other relates to the company's sustainability goals, which are common amongst some of our strategic energy management participants, which are early adopters of other energy efficiency technologies. And finally, factors that are more regional in nature, such as the electricity to natural gas price ratio and state policy. BPA does have policies that impact decisions around eligible energy efficiency when there's a change in primary energy source. We have more work to do in establishing a robust baseline framework, but our overarching goal is to help sites that are installing these technologies make the most energy efficient selection and design decisions. We're looking to partner with vendors too, who can help us understand the range of efficiency choices available. While we've been focused on fossil-fueled electricity energy sources, here's the simplest case for an industrial heat pump upgrade: a retrofit of an existing electric heating system. There's no fossil fuel to consider or worry about in the baseline. From left to right, first is a scenario where an industrial heat pump replaces a resistive electric heating system. It's a great project. It's a simple baseline decision. Our goal would be to work with a site to make the most efficient industrial heat pump selection. In this example, that's option 2. But all the savings are eligible. Here's where the complications to an electrical energy efficiency program offering arise from an industrial heat pump upgrade. A retrofit of an existing thermal heating system, which we're calling scenario 2. Northwest Power Act requirements, which are BPA's legal construct for energy efficiency incentives, requires us to take into consideration the hypothetical electrical load as either electric resistance heat, when it's a possibility, or a standard practice industrial heat pump unit, when resistance heat is not a real possibility. The site would realize the significant benefit for overall CO2 reduction, and the delta between the gray bar on the far left and any of the blue bars on the right can certainly be factored into the economic analysis of that end-use facility. Potential incentives due to the electrical energy eligible EE deltas shown on the right can certainly be factored in too. Other possibilities for incentives to the end-use facility may currently exist or will in the future. However, the program would likely only claim the incremental savings from the highest efficiency industrial heat pump. But there may be cases where a fully electrified system may be technically and financially viable and we need to weigh those decisions carefully. I have an M&V reference library I present. So BPA's M&V protocol library is extensive and detailed. It includes 12 M&V guides developed by a number of industrial experts. These are the basis for all of BPA's measurement and verification activities and are great supporting resources for ECIPs, technical service providers, and customer service energy efficiency engineers. We highlight two of the protocol documents here that most likely be applied for M&V of future industrial heat pump projects: verification by equipment end-use metering protocol and end-use metering absent baseline measurement. Considering those two previous scenarios we reviewed. Other protocol documents may apply too. Wouldn't it be great and exciting and a fun technical challenge to have an industrial heat pump project installed within a facility participating in strategic energy management? I'm sure many of you and our ESI EPT team members, Jacob, Anna, and Adria, would agree. Well, we hope we planted that seed during this presentation to pique your interest in a follow-up webinar, an industrial heat pump technical webinar that could be scheduled during the last quarter of calendar year 2022. Could be opened up to invite your industrial customers that you identify too. A survey is going to be directed your way by email to inquire of your interest in that technical webinar. It may be in the chat box. Now I can't see for the moment. There's lots of unknowns that we'll learn more about during this industrial heat pump market characterization. Ideally, the design and install with M&V during the latter time shown here. Well, I think we have time here, and I want to thank everyone for joining and participating, and thanks to Ed and Steve Martin for checking this chat box. And so thanks again, and wish you all a very productive and good day.